first, thanks to the organizers for having me here today. So, I am Chandra Shekhar for IIT Indore, and I'll be talking about probing the your astrophysics with 21 centimeter line intensity mapping bispectrum. So, this is my brief overview of the talk. So, I'll start with Epoch of Reionization, and I'll move on to discuss the line intensity mapping as a tool that can be used to probe UR and about cross correlations. And then finally, I'll move on to the impact of astrophysical scatter on the statistics and how we can use the 21 centimeter auto bispectrum to probe the scatter that can have imprints on the 21 centimeter signal. So in this evolutionary history of the universe, what we are interested in is that when the first stars and galaxies reionized the universe, so how did this process happen, and how we can probe this epoch to learn more about this. So these are some of the examples that can help us in probing this epoch. So this is the ALMA observatory, and this one is the space-based JWST mission. So this will do point source detections of the galaxies that were responsible for reionization, and this will do the most detailed observations of these galaxies. But there are certain challenges. For example, these instruments require very demanding sensitivity limits, as well as they require very high resolutions. And on top of that, they're also very expensive to operate, which means that in principle that it's very expensive to have a large volume service, which we are actually interested in to see how the large scale structures evolve in cosmic time. So there's a proposed complementary solution to this, so which we call as the line intensity mapping of galaxies. So the basic idea over here is that we basically try to make a low resolution survey of the sky that we're interested in. So we can take this large volume and chop it up into smaller regions, which we call the voxel, which is equivalent to a 3D pixel. So it has two spatial dimensions, and the other one is in the frequency, which translates to redshifts. And within these voxels, what we try is that if numerous sources lie within this voxel, then we, in principle, detect the cumulative the cumulative flux with this instrument, and by that we make a low resolution coarse grained survey of the this large volume sky. So there are certain advantages of using this method. So the first one is that we do not we give up on resolving individual galaxies, and therefore it can have far more relaxed detection limits as compared to the point source detections. And of course, since we have this advantage, then we can also do large volume surveys within a resolvable observational hours. For example, we can do square degrees observations within a couple thousands of hours. So some of the examples that that is involved in LIM experiments is, one of them is the Concerto, which focuses on this C2 line emission, which has a rest frame of wavelength of 115 micrometers, and these are emitted from galaxies. So this can be used as a tracer to map out the large volume surveys. And the other ones are, for example, the COMAP, which will also target the C2 line, and the other one is the molecular line from carbon monoxide. And this one is the Sphere X, which will target the Lyman alpha emission from the galaxies. And of course, there are many such more examples. Similarly, there are instruments which will target the 21 centimeter signal, which is emitted from the neutral hydrogen distribution from the IGN. So instruments like LOFAR, HERA, and the Square Kilometre Array, so they will target this evolving 21 centimeter signal, and we plan that this can be used to track the evolution of the IGN. So the idea here is that since we are interested in probing the EOR using multiple lines, so then this brings us to the interesting opportunity that multi-tracer line intensity mapping opens up the opportunity for doing cross correlations. For example, we can take the signal fluctuations in the real domain, and we can take a Fourier transform. So we can do this for all of the lines. And for example, if we take the C2 line emission and the line emission from the IGN, which is the 21 centimeter, and if we cross correlate them, so in principle, then we can estimate this statistic, which we call the cross path spectrum. And this has certain benefits. For example, it is more robust in as compared to power spectrum in respect to the foreground contamination, and it can also be used to track the UR history. So these kind of interesting cross correlations can be done using various line emissions. So now let me come to the issue of the astrophysical scatter that we have done in our work. So usually when we try to simulate a mock uh, uh, line intensity map of galaxies, so what we usually assume that we assume a model which relates the halo mass to a certain line luminosity. For example, in this case, we can use a correlation function that gives a one-to-one relation between the halo mass and the corresponding C2 luminosity. But in reality, this is not the case. For example, we have used the data from the hydrodynamic SIMBA simulation, which shows that you can have a significant amount of scatter between the relation between the halo mass and the C2 luminosity, and which is also true from other line emissions as well. So what it means is that in principle, this scatter will have significant impact on the statistics that we are trying to determine. For example, the power spectrum. So to study this impact of this scatter on the statistics. So what we have done is that we have fitted this scatter using different approaches. So we have taken bins of the scatter. So these purple points show the modes that which is shows the most probable distribution of the C2 luminosity, and so this black one shows this fitted line done through the purple points. And we have also done another fit, which is the using the arithmetic mean bins of the luminosities, so which we call the mean correlation fit. And using this, so what we study or see is that if we do the power spectrum for the whole simulation, which actually includes the original scatter, and compare them with the statistics in which we have no scatter but only done using the fitting functions. So we see that in both of the cases, there is a significant amount of change in the power spectrum, and of course in the mean intensity as well. So this means that scatter needs to be taken into account for making more realistic predictions of these statistics. So inspired by this, we are now interested in studying how this kind of astrophysical scatter might also impact the 21 centimeter signal. So that means in this case, what we usually assume in simulations is that we assume that this photon emitting rate is proportional to the a certain kind of a star formation model. So in this case, it is we have taken a mean relation, and it doesn't have any scatter. So it means that we have assumed the star formation rate. It is perfectly correlated to our correlated to the host halo mass. But let's say if we now want to study the impact of scatter, so we have to assume some model of scatter. So usually we assume that SFR follows a log normal distribution. And therefore, it means that since we have introduced scatter, then the star formation rate is no longer perfectly correlated to our host halo mass. So it means that our photon emitting rate is now proportional to this quantity, which is the mean star formation rate, on top of which we have added a log normal scatter. So this kind of study has been previously done. So in this example done by Hassan et al. So what they have actually shown that even if we introduce this scatter, so this doesn't have a very significant impact on the power spectrum, which is the 2-point statistic. So in this case, what they have shown here is the power spectrum for the ionization field, and they have done this for different redshifts, which has different neutral fractions. So they have assumed different models. So in one of the models, they have no scatter, and in the other models, they have realistic scatter from the simulation, as well as they have artificially introduced scatter. And in all of the cases, they studied what kind of impact they see, and as we can see that the impact is not very much drastic, as is evident from this. So we have also verified this result in our own semi-numerical simulation using Ria and Yuga. So we have studied here two redshifts with these neutral fractions. So one of them, so this solid line is the case where we do not have any scatter, and in this dashed line shows the case where we have scatter. And we observed that the maximum change in the power spectrum can vary between 4.4 and 8.4%, so which is not that much large for these cases that we have studied. So now we come into the question that whether bispectrum can actually do a better job in probing some certain kinds of signatures that this scatter might have. And we expect this because, as mentioned in the previous talk, that bispectrum can capture non-Gaussianities in the signal better than power spectrum can do. And therefore, if this astrophysical scatter does introduce any additional non-Gaussianity, then therefore, in principle, it should be possible to capture that additional non-Gaussian features with this bispectrum. So just to briefly recap, so bispectrum is the 3-point correlation function in the Fourier space, and if we follow this prescription, so then in principle we can determine all the unique triangles of the bispectrum in the Fourier space, and if we take the ensemble average of these Fourier fluctuations, then we can estimate the bispectrum estimator, which we parameterize with certain parameters. For example, the angle between the negative k1 vector and k2 vector, which is the cos alpha, the ratio between k2 and k1, and the k1 vector itself, and then we do this normalization. So to study this impact of the scatter and see on the bispectrum and see if it can actually distinguish between the models. So we have assumed a certain mean SFR relation, SFR Hilo mass relation, and we introduce a log normal scatter and assume that the scatter value is around 0.3 dex, which we introduce in the star formation rate. And then we assume that this photon emitting rate is proportional to this SFR, which follows a log normal distribution. And then we generate 21 centimeter maps using semi-numerical code for two cases. One using only the mean SFR relation, and in the other one which actually has the scatter imprinted. So in this case, what we have studied is that, so this top panel, this shows the bispectrum for all the triangle modes, which one is done only using the mean relation. So, and this middle panel is shown for the maps which actually has the scatter introduced in the start formation rate. And in this bottom panel, we see the change between these two maps. So we take the difference and then take the ratio with respect to the mean. So in this case, what we see is that for this particular redshift at this neutral fraction, so for not all the triangle modes will actually probe the imprint, but rather for certain triangle modes, we see that there can be significant impact on the bispectrum due to this introduction of scatter, and this can be as high as up to 200%. And for the for slightly lower redshift with this neutral fraction, we see that for different triangle modes, we see more drastic impacts on the bispectrum. So what we can from these preliminary results, what we can say is that bispectrum can hold this promise to actually probe this imprint of astrophysical scatter far better than the power spectrum. And what we can do further is that we can check the robustness of the results by checking for these results for other beamwidths, as well as we can study how this impact might change for varying strength of the scatter, and we can do this for multiple redshifts to see whether in which of the stages this impact might be maximal or minimal. So this is what I had, and thanks for your time.
Now it's time for questions. Hi. So my question is, how many realizations have you considered when you take the bispectrum for the scattered models?
Okay, so in this case, we actually study a single realization for both the scatter and the mean, but yes, it can be extended for multiple realizations.
You should take multiple realizations.
Yeah,
right?
yeah. So
because
these are
the scatter is random,
right?
And you need to see whether the same K modes are affected by the scatter or they are like scattered altogether in different K modes.
So whether
if it is, then I don't know how can you distinguish.
Right, sure, yeah. So these are for now these are preliminary results. So we'll extend this doing multiple realizations. Thanks.
So in this slide itself, the first and second row. So why the upper right corner? The squeezed limit has a certain higher value, 10 to the power 4, compared to other. What could be the reason? Because I see most of the part is yellow. That is.
Yeah. So because this corner actually represents that squeezed limit triangle, right? So where you actually have because K2 by K1 is almost 1, right?
Yeah, that I understand. I mean, can we extract any physics or any physical process from?
In principle, it might be possible. Yes, we have to study that.
And that is high.
It will be picking up small and extremely large length scale correlations. So that tends to have a larger magnitude. That is what we get. I do not have any other answer to that particular.
Yeah, so this needs to be studied actually.
Last one questions.
So when you add your scatter,
Yeah.
you add it randomly without any information about the environment from Simba. Is that correct?
Yeah, so in this for the 21 centimeter case, this is we introduce it artificially.
Right. Is there any effect of this environment on the C2 versus, the luminosity versus mass relation? Environment in the sense galaxies in
mean-
the similar environment will have similar relation, less scatter kind of thing.
Okay, so you mean if we take this realistic scatter?
Yeah, but this is scatter without any environmental information, because a 10 hello mass galaxy could be in different environment and the other 10 could be in the completely different environment.
Yeah.
So that that may affect the power spectrum, right? Because if the environmental dependence is not accounted for.
Yeah, but ultimately what we are actually interested in is that whether these environmental effects, how they play this role in the these two quantities, that is halo mass and the LC2, because that will finally.
In the scatter that you see is
Yeah.
just independent of environment. You took all the galaxies in the Simba simulation and plotted them.
Yeah. So and we just plot them in halo mass and the luminosity.
Yes.
Yeah.
Environmental could be another
Yeah.
thing
So
you can
those
explore.
effects actually they should be imprinted in the this scatter in itself. Actually.
Sure. Yeah, we can discuss later.
Right.
Okay, thanks, Chandrasekhar again.